You've now learned how to create an equivalent circuit model of battery cell dynamics that includes state of charge, open circuit voltage, ohmic resistance, and dynamic polarization. And you've seen how to model the circuit with continuous time ordinary differential equations, and also how to convert those into discrete time ordinary difference equations. But in order to use the model for any purpose that would make sense, we still require knowledge of the parameter values or the constants in the model. So that is, we need to know what is the open circuit voltage relationship of the cell versus state of charge, what is the coulombic efficiency, what is the series resistance R0, and so forth. So in this lesson, you will learn a simple method to find approximate model parameter values when you're using an equivalent circuit model that has a single resistor capacitor branch in it. The method does not work with a more complicated model, such as one that has multiple resistor capacitor branches, or some of the other features that you'll learn about later this week. But it does provide a starting point, and so you'll see a simple method to find model parameter values, and then over the coming weeks you'll learn methods to improve and find even more accurate parameter values for the model equations. So I think it's still a worthwhile exercise to think about how we could very simply find some parameter values of this model. Remember the equations that we've developed to date to model a battery cell. They're reproduced on this slide. We have one equation that describes how state of charge changes versus time. We have another equation describing the evolution of the resistor current in a resistor capacitor branch, and a final equation describing how to compute the cell's terminal voltage. In order to be able to evaluate these equations, all of the constants in the equations must be known. So for example, we need to know the cell's total capacity Q. And this can be found in the laboratory by starting with a fully charged cell according to manufacturer specifications for how to charge a cell, and then discharging that cell down to 0% state of charge and recording the quantity of ampere hours that were removed from this cell in the process. That's the discharge capacity. We can also find the coulombic efficiency eta in a relatively simple way. We start with this cell completely discharged at 0% state of charge, and then we charge this cell up to 100% state of charge using, again, the manufacturer suggested way of doing so. And that gives us a charge capacity, how many ampere hours of charge were needed to do that. And if we take the discharge capacity and divide by the charge capacity, that gives us the coulombic efficiency of this cell. We also need to find the open circuit voltage relationship of the cell versus state of charge. You'll learn a better way of doing so next week, but one way that we can do this is, again, to start with a fully charged cell and then quite slowly discharge the cell down to 0% state of charge and measure what we call the discharge voltage at every state of charge in doing so. And then we do the opposite. We start with a fully discharged cell and we slowly charge all the way up to 100% state of charge, and we measure a charge voltage at every state of charge while we do so. And because of the resistances of the cell, the discharge voltage will be below open circuit voltage and the charge voltage will be above open circuit voltage. But if we compute an average of the discharge and charge voltages at every state of charge, we will have a pretty good approximation to the open circuit voltage relationship of this cell at every state of charge value. Again, there are some nuances that we can think about to improve on this method, but that's a pretty good place to start. So if you think of those equations on the previous slide, we now have Q, we now have eta, and we now have the open circuit voltage relationship. But we still require ways to determine the series resistance R0 and the resistor and capacitor values of the circuit as well. And one way to find these values is through conducting a very simple laboratory test on a physical battery cell. This laboratory test takes a cell and subjects it to a short constant current discharge pulse, and then removes that current and allows the cell to rest at a zero input current value. And during this test, we record the terminal voltage as a function of time. So the figure on the right of the slide shows an example result of voltage versus time that we might record from such a test. You can see that the cell was allowed to rest at a high state of charge for about 5 minutes, and then the cell was subjected to a constant current discharge pulse for about 15 minutes, and that lasted until the overall time was 20 minutes. And finally, the input current was removed from the cell, and the cell was allowed to rest for about 40 minutes, and we recorded voltage throughout the entire test. In order to find the parameter values we desire, we can note certain specific things from the figure. First, we notice that the instantaneous change in voltage at time 20 minutes is at the time that the discharge current has been removed from the battery cell. If you examine the equations that describe cell voltage, you'll see that they're a function of state of charge and the resistor R1 current and the voltage drop across resistor R2. But from the state of charge equation of the model, we recognize that if we change the current, the state of charge does not change instantly. It changes as it integrates current over time. So when I have been discharging and remove current, the state of charge actually stays constant for the remaining 40 minutes of the test. So that does not explain why voltage changed instantly at time 20 minutes. And if you look at the resistor-capacitor equations, it turns out that the capacitor voltage also cannot change instantly. So the only thing in the model that can change instantly when current changes is the voltage drop across resistor R0. So therefore, the instantaneous change in voltage at time 20 minutes must equal the magnitude of current change multiplied by the resistance. That's the magnitude of the change in voltage. And we can measure this magnitude of change in voltage. In fact, we have, and it's plotted on this figure. And we can measure the change in input current, most likely because we were the ones subjecting the cell to a constant input current and then removing it, so we know what that change is. And then we can compute the change in voltage magnitude is equal to the resistance times the change in current. Or we can say that resistance is equal to the change in voltage divided by change in current. Notice the absolute value signs. This is because we know resistance must be positive, and we might be a little bit careless in how we think about a change in voltage or a change in current versus time. You can do it very carefully, of course, but it's easier to think about it just as the magnitude of the change in voltage divided by the change in current. So we use that method with this test to find the internal resistance R0. And once we know R0, we can next approximate the value of resistance R1. We use exactly the same data from exactly the same test, but now we consider the steady-state voltage change after the pulse is removed instead of the instantaneous voltage change after the pulse is removed. So I've put the same figure on this slide, and I show you the equations for the steady-state voltage change, and I don't prove it here, but it's possible with some linear circuit analysis to show that the change in voltage is equal to the R0 plus R1 all times the change in current. So we can measure, as you can see on the right-hand side of the slide, the up-down arrows are showing this delta V infinity, or the steady-state voltage change. And we know R0 because we computed it using the equation from the previous slide, and we know delta I because we subjected the cell to a certain current and then removed it. So based on all of that, we can rearrange our expression and solve for R1. So when we do that, we have the steady-state change in voltage is equal to R0 plus R1 times the magnitude of the change in current. Rearrange and solve for R1. The final unknown parameter value in our model is the capacitance. And in order to find this value, we consider the duration of time required for the voltage to decay into its steady state or rest value. So once again, we look at the same figure. And from linear circuit analysis, we can approximate, it's not perfect, but approximate, that the time it takes for a resistor capacitor circuit to reach a steady state value is about 5 time constants, or about 5 times R1 times C1. And we already know R1, and we can measure this time from this test, and from that we can deduce the quantity of C1. So let's do an example. We'll use exactly the same figure, so there's nothing new here. But for this laboratory test, I wrote down what the values were. So the cell was resting initially, and then I subjected it to a 5 ampere discharge pulse for 15 minutes, and then I removed that. And so the change in current in magnitude was 5 amperes. And then I measured, well, how much did the voltage change instantly when current was removed? And that was 41 millivolts. And then how much did the voltage change between its minimum value and its steady state value? And that was 120 millivolts. So we can use these values. That's what we need in order to compute the R0 and the R1. So we compute R0 to be equal to the absolute change in voltage divided by the absolute change in current. So 41 millivolts divided by 5 amperes, and you get 15.8 milliohms as that resistance. No, sorry, you don't. You get 8.2 milliohms. And then you say, well, what is R1? Well, I take the steady state change in voltage of 120 millivolts, and I subtract from that R0 times delta I, which was 41 millivolts, so we have on the order of 80 millivolts left over. And I divide that by 5, and we have this 15.8 milliohms is the value of R1. To find the capacitor value, we have to approximate how long is required for this cell to reach steady state. And here I'm saying it's about 40 minutes. It's from about time 20 to about time 60 minutes. And that's considered to be 5 time constants. So 40 minutes is 2400 seconds. And so 5 times R1 C1 is 2400 seconds. And we already found R1, but we could divide 2400 by 5 and get that's 480. So C1 is 480 divided by R1. We've already found R1. So using that value, we see that C1 is about 30 kilofarads. And that's our model. We've found the capacity, we've found the Coulombic efficiency, we've found the open circuit voltage relationship, we've found R0, R1, and C1 for the model. So to summarize, you've seen a very simple procedure for approximating the parameter values of a model having a single resistor capacitor branch. In our laboratory, we used a calibrated current source to do the 5 amperes, but you don't even really need to do that. You simply need to put your battery cell under a load, maybe just have just a standard resistor connected to it, but also have an ammeter measuring what the current is through that load, and then have a data recorder that can measure the voltages of the cell versus time. So for a very, very inexpensive setup, you can find these parameter values. So here we've assumed that we've performed a simple discharge test and a charge test to get approximate values for total capacity and Coulombic efficiency and the open circuit voltage functions. The follow-on pulse discharge test can be used to find the values of R0, R1, and C1. You might wonder how well this method works, and the way to check that is to use this model, these equations, and simulate using the same profile of input current versus time what the model predicts the output voltage to be versus what the actual measured output voltage happened to be in the real test. And here on this figure, the blue line is the actual test data taken from the cell, and the black dashed line is the simulation result of the model that we just created using this simple method. And it has some characteristics which are really good and some that are maybe a little bit imprecise still. So it started out at the right voltage, and then when the discharge current was first applied, the voltage drop is again a very good voltage drop. But then over the next 14 and a half minutes, you can see that the black dashed line does not follow the blue line really, really closely, although it does in a very approximate way. When the current is removed, the black dashed line does jump up about the correct amount, but then the time constant for it to decay to the open circuit value is, again, not perfectly right. It probably decays a little bit too quickly, honestly. And so you can do some things at this point. You can manually adjust the parameter values of the model to see if you can improve it. Or you can use an optimization procedure to see if you can improve it. So here I used a process that we're going to look at in a couple of weeks to also build an equivalent circuit model for this cell that used not only one pair of resistors and capacitors in the Thevenin model, but three pairs. So R1, R2, R3, C1, C2, C3, in addition to the series resistance R0. And I trained that model, and its prediction is given by the red dash line, which is almost directly on top of the blue line. And it's much better. It allows us to get a combination of time constants because, in actual fact, we learned from the Warburg impedance lesson, there are multiple time constants going on, not just one. And it's perhaps incredible, if you think back to that lesson, at how well the three resistor capacitor model approximates this voltage profile, given the fact that we know that to do it ideally we would need an infinite number of resistors and capacitors. So, using a pretty simple model, we can get actually quite a good result. So which model would you use? Would you use the simple ballpark model with one resistor capacitor, or the three resistor capacitor, or something else? And I think the answer to that depends on your application. And does your application demand really high fidelity, high accuracy predictions? Or does your application demand really, really simple, fast computations? And there's a trade-off usually between how quickly we can compute a result and how accurately we can compute a result. So either of these models actually could be perfectly good. Just depends what your application happens to be. So that brings us to the end of this lesson. In the remainder of this week, you're going to learn about one more phenomenon that's found in lithium-ion battery cells that we've not yet modeled, and by modeling this phenomena, we can improve the performance of our models considerably in some cases. And this phenomena that we will model is called hysteresis, and it turns out to be a pretty dominant effect in lithium iron phosphate cells, for example, and still existing in other cell chemistries as well. So that's what we're going to look at next.